Welcome to the Security Buddy. Today we will discuss the fundamentals of quantum computing. First, we will discuss why do we need quantum computers. Let's think of two librarians. One can read only one book at a time. Irrespective of how fast she reads the book serially one by one. And the other librarian can read every book in the library simultaneously. The first librarian, irrespective of how fast she can read, is limited by a linear process. The other librarian, as he can read every book in the library simultaneously, can read many more books than the first librarian. A classical computer, irrespective of how powerful a supercomputer it is like the first librarian. It is limited by linearity. Irrespective of how fast it can operate, it still reads and processes data serially. A quantum computer is like the second librarian. It is equipped with simultaneous power which enables it to solve problems faster. Let's consider a computational problem. There are n number of people in a room. There is a dinner table. Certain people cannot sit beside certain people, and we need to find an arrangement where every person sits comfortably for dinner. If we try to solve the problem using a classical computer, there will be millions or billions of combinations. And as a classical computer cannot operate in parallel, it has to evaluate these many combinations serially, which may even take thousands of years. A quantum computer can use superposition to operate in parallel and evaluate all these combinations simultaneously. Therefore, irrespective of how powerful a classical computer is, a quantum computer is much faster and more efficient than any classical computer. Now, we will discuss the basic unit of quantum computation, qubit. A classical bit is like a coin lying flat on a table. It is either heads or tails. There is no in between. Now, let's say we spin the coin on the table. Is it heads or is it tails or is it both? It's neither. It's in a state of superposition. When the coin is spinning, it holds a complex mathematical relationship with the probabilities of being heads or tails. Let's say the probability of the coin being heads is mod alpha square and the probability of being tails is mod beta square, where alpha and beta are complex numbers. At this point, if we specify heads with the state Ket0 and specify tail with the state Ket1, then the state of the coin psi can be specified as alpha Ket0 plus beta Ket1. When the coin is spinning, it is in the state psi. However, if it stops spinning, the quantum state of the coin psi collapses and chooses Ket0 or Ket1 with the respective probabilities. This is why quantum computing is so difficult. We have to perform all the complex maths while the coin is still spinning without disturbing the coin, so that the quantum state of the coin does not collapse. Here, the coin is analogous to a qubit. The spinning state of the coin is analogous to the quantum state of the qubit. Qubit is a basic building block for quantum computation. Now, let's take a deep dive into this topic. We write a quantum state using a gate vector. If a qubit is in the state gate 0, we write it as gate 0. And when a qubit is in the gate 1 state, we write it as gate 1. And when the qubit is in a quantum state psi, we say that the qubit can be in the state gate 0 with the probability mod alpha square, and it can be in the state gate 1 with the probability mod beta square, where alpha and beta are complex numbers. How do we visualize a qubit? We visualize a qubit using the Bloch sphere. The Bloch sphere is a unit sphere that is used to represent a qubit geometrically. If a qubit is in a pure state, then we can represent the state of the qubit by a point on the surface of the Bloch sphere. If a qubit is in a mixed state, then we can represent the state of the qubit by a point inside the Bloch sphere. The radius of the Bloch sphere is 1. The z-axis shows gate 0 at the top and gate 1 at the bottom. This shows the probability of the qubit measuring gate 0 or gate 1. The x-axis represents the real part of the state of the qubit. The y-axis represents the imaginary part of the state of the qubit. In this example, if we measure the qubit can be gate 0 or gate 1 with equal probability. In fact, the state of the qubit is 1 by root 2 gate 0 plus gate 1. The state of the qubit makes an angle theta with the z-axis and phi with the x-axis. In that case, we can write as following. For example, psi is gate 0 plus gate 1 by root 2. Therefore, angle theta is pi by 2 and angle phi is 0. Now, let's discuss what superposition, entanglement and interference are. What is quantum superposition? We already discussed what quantum superposition is with an analogy of a spinning coin. If a coin is lying flat on a table, it can be in the state of heads or tails. If the coin is in heads, let's say it is in state gate 0. If it is tails, then it is in state gate 1. When the coin is spinning, it is in a state of superposition. Let's say when it stops spinning, the probability of heads is mod alpha square and the probability of tails is mod beta square. In that case, we can say that the coin is in a state of superposition that can be described with the following quantum state. Similarly, if there are two qubits, they can be in a state of superposition that can be described as follows. Please note that in this case, the probability of the qubits being gate 00 is mod alpha 0 square. The probability of the qubits being in state K01 is mod alpha 1 square. The probability of the qubits being in state K10 is mod alpha 2 square, and the probability of the qubits being in state K11 is mod alpha 3 square. What is quantum entanglement? Let's say I have two coins in my hand. There is an invisible link between these two coins. If one coin is heads, the other coin will also be heads, and when one coin is tails, the other coin will also be tails. Let's say the invisible link is so deep that the two coins behave in this way even if they are miles apart. In other words, both coins share a single existence. If both coins stop spinning and one coin shows heads, then we can be certain that the other coin is also heads without even measuring the outcome of that coin. In the subatomic world, it is called quantum entanglement. This quantum entanglement is a primary feature in quantum mechanics. It is not present in classical mechanics. Physical properties like spin, momentum, position, polarization, etc. of entangled particles are seen to be in perfect correlation. In a classical computer, the measurement of one does not affect the measurement of the other. Therefore, unless we measure all the bits, we do not know what the data is. However, in a quantum computer, qubits can be in an entangled state. As a result, if we measure one particle from a group of entangled particles, we know what the other particles of the entangled group will be. Now, let's look at a real example. Let's say there are three qubits that are in the following state. These three qubits are entangled, and we call the quantum state the GHZ state. If we measure one qubit and it's in K0 state, we know that each of the other two qubits is also in K0 state. If we measure one qubit and it's in K1 state, we know that each of the other two qubits is also in K1 state. Quantum entanglement is heavily used in quantum communication, quantum cryptography, and quantum teleportation. With the help of quantum entanglement, we can achieve many tasks that are otherwise impossible. Now let's discuss what quantum interference is. Much like sound waves, a quantum state has its peaks and valleys. They are mathematically known as quantum phases. When the peaks of two waves coincide, they combine to get a larger wave. We call it constructive interference. In quantum algorithms, we often leverage this quantum interference so that peaks of relevant waves coincide to give a larger wave that gives the correct answer. Similarly, when the peak of a wave coincides with the valley of another wave, they cancel each other. We call it destructive interference. In quantum algorithms, we often use destructive interference to cancel out the incorrect answers. Now, let's discuss quantum hardware. An American theoretical physicist named DiVincenzo published a research paper named Topics in Quantum Computing in 1996. This paper outlines 5 minimal requirements for implementing a quantum computer. Any experimental setup that wants to implement quantum algorithms successfully must satisfy these criteria. They are: a quantum computer should be able to initialize qubits to a simple fiducial state. For example, before running a quantum algorithm, we may need to initialize a qubit to the state K0. A quantum computer should be able to do so. A quantum computer often uses thermalization or active reset for this purpose. In the thermalization process, we let the qubits wait for a long time so that they decay to the ground state or K0 state. In active reset, we apply a pulse to reset a qubit to the ground state. The second criteria is that a quantum computer should be able to implement a universal set of quantum gates. Often, pulses with the appropriate frequency, shape, amplitude, phase, and duration are used to interact with a qubit. This changes the qubit wave function in a desired way. If a pulse interacts with only one qubit, we call it a single qubit gate. If it interacts with two qubits, it is called a two-qubit gate, and so on. A quantum gate can be a multi-qubit gate, but it can be decomposed or approximated by a set of single qubit or two qubit gates. We call those one qubit or two qubit gates universal quantum gates. The third criteria is that a quantum computer should be able to measure a qubit without disturbing the quantum state of the other qubits. A quantum computer often measures a qubit by applying a pulse to a qubit. After that, we observe the change in the reflected pulse, which is modulated by the quantum state of the qubit. Please note that due to the nature of quantum mechanics, when we measure a qubit, the qubit wave function collapses to basis states. The fourth criteria is that a quantum computer should be scalable with well-characterized qubits. The different quantum states of a qubit, namely K0 and K1, need to be well distinguished for that purpose. The energy separation between any two different quantum states of qubits should not be too close. For example, if a qubit can be in states K0, K1, K2, etc., then the energy separation between K0 and K1 should not be too close to the energy separation between K1 and K2. If not, then quantum computations will fail. When there is noise, the energy separation of two quantum states should be well above the noise level. There can be thermal noise or quantum noise. For example, thermal noise is proportional to kT by Q, where K is Boltzmann constant, T is temperature in Kelvin, and Q is elementary charge. Therefore, if the qubit energy separation is 0.02 MeV, then we should maintain the temperature of 10 to 20 millikelvin. Energy separation of 0.02 MeV is equivalent to 230 millikelvin of thermal noise. Therefore, the actual thermal noise is maintained at about 10 to 20 millikelvin so that the energy separation remains much higher than the thermal noise. A dilution refrigerator is used for that purpose. And the fifth and last criteria is that the decoherence time should be long and relevant. It should be longer than the gate operation time. A qubit may not interact with any given pulse, and yet it can lose information by interacting with the environment. This is called quantum decoherence, and the duration for which a qubit can maintain its state without any intentional interaction is called the decoherence time. The time constant of how fast a qubit decays from an excited or Ket1 state to the ground state or Ket0 state is called T1 decoherence time. And the time constant of how fast a qubit decays from a superposition of Ket0 and Ket1 to a classical mixture of Ket0 and Ket1 is called T2 decoherence time. A qubit needs to have a long decoherence time so that it can perform enough computation before its state decays. Thus, the decoherence time should be longer than the gate operation time. Different types of hardware are used for quantum computers. The most commonly used hardware is a system with superconducting qubits. Companies like IBM and Google use this type of quantum hardware. Companies like IonQ and Quantinuum use trapped ion systems. Some quantum computers use photons as qubits. These photonic quantum computers do not always require extreme cooling. Very recently, the focus has shifted from physical to logical qubits. Quantum computers often group hundreds of physical qubits together, and the group of physical qubits works as a logical qubit. Individual qubits are noisy, but when we group them together, they act like a perfect logical qubit. Now, let's discuss real-world applications of quantum computers. Now, we are in an era where quantum computers have begun moving from demonstration to deployment in specific high-impact niches. Some companies like Biogen have already begun using quantum computers to accelerate research into new medicines. Discovering a new medicine often takes billions of dollars and a decade of testing. Quantum computers can effectively reduce the cost and timeline for new drug discovery. Using quantum computers, researchers can simulate the structure of molecules at an atomic level. Classical computers often struggle to do so as the math for subatomic interactions is extremely complex. As a result, using quantum computers, researchers can understand in a better way how a newly discovered medicine will bind to a protein. Quantum computers have vast applications in cybersecurity. We use encryption algorithms like RSA or elliptic curve cryptography because problems like integer factorization are technically infeasible to solve in classical computers. However, quantum computers can solve these problems easily. The threats to cybersecurity are immense nowadays. As a result, many companies are investing billions of dollars in quantum computing research. Now, if we consider material science and green energy, quantum computers can simulate new materials that were previously intractable. As a result, researchers are able to find new battery chemistries that can double the range of electric vehicles. Researchers are using quantum computers to develop new, more efficient, porous materials that can absorb carbon dioxide directly from our atmosphere. Quantum computers can also be used in supply chain and logistics optimization. Companies like Telefonica have started using quantum computers to optimize delivery routes in real time. Quantum computers can also be used to optimize how millions of items are packed and shipped to minimize fuel and time. Quantum computers can be used in financial modeling, where even a 1% improvement in accuracy may be worth billions. We can use quantum computers for portfolio optimization, where there are thousands of variables always changing. Using quantum computers in risk assessment can predict market crashes or credit defaults in a better way. Quantum machine learning can also be used to identify patterns in transaction data that lead to financial fraud. Even classical AI might miss detecting such patterns. Please note that as of 2026, we don't use pure quantum computers. We often use hybrid classical quantum architectures. In hybrid classical quantum architectures, classical CPUs or GPUs do the heavy lifting for data management, and quantum accelerators are called to do only the parts of the problem that are technically infeasible in classical computers. So, what is the road ahead? In 2026, the industry has moved past mere experimentation with quantum computers. We are now in the era of quantum utility, and quantum programming software development kits and frameworks like Qiskit or Circuit are the primary engines driving this shift. We can use Qiskit or Circuit to write our own code in quantum programming. For example, we can install the Python-based package Qiskit and start constructing quantum circuits. We can use Qiskit runtime to execute that code on IBM quantum systems. We can also use Qiskit Air to run quantum circuits on simulation backends before running them on actual quantum processors. In our next video, we will discuss how to use Qiskit for quantum programming. I hope this video has helped viewers in having a basic understanding of quantum computers. Thanks for watching.